Okay, this next video on the Applied Maths series is about statistics, and we're going to start statistics with an introduction to the ideas of central tendency and dispersion. Before we do, a quick word about stats itself. The word statistics comes from the Latin word status, which means position, because the most basic forms of statistics involves finding the most typical position of things. There's different ways of doing this. You can imagine the three people standing in a line. Which one's the one in the middle? It's the second one, right? But if you were to look at it a different way, if you were looking at how much money's in their pockets or what height they are or weight they are, the middle one could be the guy on the left or the right. It depends how you measure it. So there's different ways to measure central tendency. Central tendency measures, they measure the position at which a bunch of data tends to center around. That's why it gets that name. In everyday English, we would usually call this the average. But in maths, unfortunately, an average is a bit of a vague term, as we'll find out. There's three different ways to do it, or three main ways to do it. They're called the mean, the median, and the mode. So we'll start with the mean. This comes from the French word, pardon my terrible pronunciation, but I think it's mean, which is French for middle. So this is the measurement that most people think of when we say the word average. And there's different ways of doing the mean. It depends on the context. We're going to look just at the arithmetic mean for now. And the symbol for that, the mean, is either that Greek letter there, mu, or the x with a bar across it, x bar. We use mu when we're getting the mean or average of an entire population. For example, if you're measuring the average height of everybody in the UK. We would use x bar when we're getting the mean of a sample, like 1,000 people from the UK. Population is when you have a value for everybody, and a sample is when you don't have all the possible data and you're just trying to extrapolate the information you need from a smaller group. So to calculate the mean of an entire population, it looks like this. Don't worry about the one on the left, which is basically the same as the one on the right, just a bit more detail. Let's look at the one on the right first over here. Mu is equal to sigma x over n. So sigma, if you remember, just means add all the values of whatever. So we add all the values of x, all the different numbers that we've got in our data, add them all together, and then just divide by however many objects there actually are, called n. The formula on the left is the exact same thing, just in more detail. It says x subscript I. So each item can be given a position in the data set, and that position has an index we can call I. So we add up all the x's in the different positions I, and that position I goes from the first one to the last one. It's just a long form way of saying the same thing, so don't get too upset about the layout of that formula. Now, if you want to calculate the mean from a sample of the population, then x bar is sigma x over n. We use a lowercase n in this case, but it's the same idea. Calculate mean the same way, whether it's a population or a sample. So in other words, just add up all the values in the data set and divide by the number of items in the set. For example, here's a set of 5 things that are on sale. The value there, it could be pounds or dollars, whatever. 4, 5, 8, 10, and 12. What's the average? Well, sum up all the x's and divide by n. There are 5 items, so n is 5. If you add up all those 5 values, 4 plus 5 plus 8 plus 10 plus 12, I get 39. Divide that by the 5. The mean is 7.8. You can also have a weighted mean. You might want certain values to be considered more important or less important for whatever reason. It could be the importance of certain data, like maybe certain items are more likely to spawn or whatever. So they have more weight. Each data item, each element in the set is not only given an actual value, but also a weight. So when you do the sum, all you do is multiply each value by its weight. So x for the item multiplied by the weight for the item, and you divide by w, which is the sum of all the weights, total weight of all the items in the set. Then we've got median. Now median comes from Latin instead of French. I don't know why we switched, but Latin word medianus, which also means middle, unfortunately. So mean and median mean the same thing in the language they come from. But in this case, the median is literally the middle one. So in for our example from earlier with 3 people, we pick the second person. That's kind of what median is doing. So the thing about median is, though, if you pick the one in the middle, if you've got an odd number of items, there is one item exactly in the middle, and here's how you find it. The subscript is n plus 1 over 2. So let's say you've got 3 people, n would be 3. 3 plus 1 is 4. 4 over 2 is 2. So the middle one is the second person. But sometimes you get an even number of items, and then there's 2 things in the middle. And if you want to get the mean, I should say median, sorry, if you want to get the median of these, then you take the one on the left of the middle, so that's the subscript is xn over 2. And you take the one to the right of the middle, which is xn plus 1 over 2. So let's say there's 4 people. That would be x of 4 over 2, which is x of 2, and x of 4 plus 1 over 2, which is the 2.5. So that would be rounded up to 3, I guess. So between the second and the third person, add them both together, divide by 2, you get the average of those 2, and that's your median. So slightly more involved if there's an even number of items. So let's imagine, for example, a set of items on sale again. There's 5 of them, same 5 again. And because this is an odd number of items, n plus 1 is 5, 5 plus 1 is 6, 6 over 2 is 3. Take the value of the third item, x3, which is this guy here, 8. That's your median. The third way of doing it is called the mode. And this is from the Latin word modus. This one means measure. And the mode is whichever number is most common in your data set. So there isn't really a formula for this, unfortunately. You just have to count how many there is of each number, and whichever number has the highest count, that's your mode. Hopefully there's only one number that appears more than the rest. If so, then your data is called unimodal. But sometimes you get multimodal data. For example, in this set here, the number 2 appears twice, and the number 4 appears twice. So if you count them all up, 2 and 4 are both modes of this data. And sometimes there's no mode, or if you look at it another way, every number is a mode. Most commonly this happens if every item is unique. So each thing appears once, which is the same amount as everything else. So there's no mode, or everything's a mode, whichever way you want to look at it. If we're all special, then nobody's special. So that's all about averages. So the next topic is measures of dispersion. So dispersion is how spread out your data is, which can be valuable to know. So there's a bunch of ways of doing this. I'm just going to pick these 4. There's plenty more, like interquartile ranges and so on. I'm not going into those. We're looking at range, variance, standard deviation, and mean absolute deviation. So range, this is the simplest measure. It's also the least useful, but it's dead easy to work out. You just take the biggest value and the smallest value and subtract one from the other. So remember, your subscript is the index. The first value would be x0. The last value would be xn. And so if you subtract the first from the last, assuming they're in order, of course, so that would be 19 minus 3. So x9, x9 is that one there, x0 is that one there. 19 minus 3, our range is 16. Simple. The variance is not so simple, and you might tell this by the symbol we use for it. It's either s squared or lowercase sigma squared. So why 2 different names? Well, if it's the variance of a sample, let's say it's 1,000 people instead of the whole country, then the variance would be called s squared. But if it's the variance of everybody, if you've measured everybody in the country, then that's the population, and we call it sigma squared. The reason for that is worked out differently. Here's a technical definition. The variance is the mean of the squares of the differences between the data points and the mean. If that sounds too technical for you, I don't blame you. We'll look into it though. This measures basically how far each data point is from the mean, and then that distance is squared, and we get the average of those squares. The formula for doing this is slightly different between a population and a sample, because the reason for that is, well, if you've got a population, again, that's typo. If you've got a sample, if you've got a sample, then the variance is by definition an estimate, because the mean is not going to be exactly the same mean as if you had the whole population. So to get the exact variance of an entire population, this is the formula. Sigma squared is equal to the sum of all of the x minus mu squared divided by n. So x is each individual value, and if you take each individual value, get the distance between that and the mean by subtracting it. Now, unfortunately, some values will be greater than the mean, some values will be less than the mean. And so if you're subtracting, you end up with some positive values and some negative values because they're to the left or right of it. And they will cancel out. To avoid that, what we're going to do is square all of them. Anything that gets squared, the negatives will disappear, and you'll be left with a number that measures, in an absolute way, the distance from the mean. And just don't forget to divide by however many objects you've got. For example, here's 3 objects, 3, 5, and 7, and the mean is 5. Just add them up, 10, 15, 15 divided by 3, 5. So our variance there, sigma squared, is x minus mu squared over n. So mu is 5, we just worked that out. N is 3 because there's 3 items in the sample. In the population. So take each one individually. 3 minus 5, 5 minus 5, and 7 minus 5. So that's negative 2, 0, and 2 when you work them out. Square each of those, otherwise they would cancel out. So minus 2 squared is 4, 0 squared is 0, 2 squared is another 4, 4 plus 4 is 8. 8 divided by 3, 2.666, repeating. So that's our variance. It might seem like just a bunch of numbers right now, and in a way, kind of it is. Now, if you want to work out the variance of a sample, this is an approximation because we don't know the exact mean of all the data that's out there by definition because we've only got a sample. So that's why it's got a different symbol, s squared. And instead of mu, you've got x bar. Instead of capital X, capital N, you've got lowercase. But it's the same formula with one difference. This is a correction which is made. There is, I believe, some mathematical proof as to why this is the right way to do it, which I'm not going to go into because this is applied maths. But essentially, you don't divide by n, you divide by n minus 1. So, with the same data, if these 3 pieces of data wasn't all of the data you could possibly have, if it's just 3 you were picked out of a larger data set, then the mean is still 5 because it's still the same data. But if you do all of these subtractions, 3 minus 5 squared, 5 minus 5 squared, 7 minus 5 squared, you get minus 2 squared, plus 0 squared, plus 2 squared, still adds up to 8. But you're not dividing by n anymore, you're dividing by n minus 1. So that's 3 minus 1 is 2, and 8 divided by 2 is 4. If I can take a quick step back, the variance of data, which is the whole population, all of the data you could possibly have, you will get a smaller amount of variance. Because if you only have a sample, we can't guarantee how accurate that sample is, so there's a larger variance. Now, variance on its own, like I said, it doesn't really tell us all that much. It can be useful on its own because you can compare the variance. If you have 2 different samples, you can see how dispersed one sample is compared to the other, and that might be useful. But because it's squared, it's not in the same units as whatever you're measuring. Let's say you're measuring the height of a person. So there might be a variance of, let's say, 2 inches, but that's, oh, actually, sorry, you wouldn't even say that. You'd say a variance of 2. You can't say it's 2 inches because it's squared. You've taken a height and squared it, and that's kind of meaningless. We don't have square heights. But it has to be squared because otherwise the positive and negative numbers would cancel out and the variance would always be 0. We'll come back to that in a bit. But the next topic is standard deviation. Now this again has 2 different names, S or sigma. If you're paying attention, that's pretty similar to S squared and sigma squared. So to get around that square problem, all we do is get the square root and they cancel out, and that's why this squared bit disappears and it's S or sigma. So this is called standard deviation. Here's the formula. So the sigma squared that we just worked out, we just put the square root around it. And we worked that out by doing this formula. So I've expanded that. You get the square root of all the sums of the distances from each item from the mean squared over n. It's starting to get pretty complicated. And again, of course, you've got a separate, slightly different formula for the standard deviation of a sample. Now, in general, most values in a data set will fall within the standard deviation. I think it's about 68% roughly you would expect in most cases. In other words, for example, if the standard deviation S is 7, then most of your data should be no more than 7 units away from the mean. Now, if you have thought about this, you may have realized, well, why do we have to square it? Why can't we just take the absolute value? And that, yes, you can. That's called the mean absolute deviation. So it's a simpler approach than squaring it and then getting the square root. Just get the absolute value, get rid of any minus signs. So absolute, if you may remember, is indicated by putting a bar to the left and right of a number. So we calculate x minus x bar, x minus the mean, so distance from the mean, but then take it as an absolute value so any negatives disappear. Don't forget to divide by n, like you did with the other formulas. So MAD is less affected by outliers that are very high or low in the data, but standard deviation can be used to calculate something called a confidence interval and related topics. This measures reliability of the data quite well. So they both have their different uses, and I think I would say standard deviation is probably slightly more useful in most cases. We're nearly finished. Now, the standard error of the mean. This happens when you take multiple sample sets from the same data. Again, let's take the example of measuring the height of everybody in the UK. You could take a sample of 1,000 people, then a sample of another 1,000 people. And each set of sample data will have a slightly different mean, slightly different deviation, because they're going to be different people. They can't all accurately measure the population, so the mean of the first sample will be different from the mean of the second. They can't both be right. In fact, they're probably both slightly wrong. So each sample mean will be different from what the true population mean was. If you had the resources to measure the height of every individual in the country, you could get the actual mean. And both of those two samples would be slightly different from it. That is the error in that mean, how wrong it is from the actual mean. And it's almost guaranteed to be there in any large sample. So the standard error of the mean measures how accurate we can expect our sample to be. Your sample mean, beg your pardon. Now, there is only one formula for standard error. The reason for that is if you have the mean of the whole population, then by definition there can be no error because your actual mean is the one you've worked out. So the error will be zero, guaranteed. So standard error makes no sense if you're measuring the entire population. So to work out standard error, x bar is used instead of mu because it's a sample. It has to be a sample, so that's x bar. You take the standard deviation and divide by the number of items, but this time you do a square root of it. And again, I'm not going to go into the proof of why that's the way it is, but I'm sure you can find videos on that out there if you have to. Here's an example. 5 data items, 10, 12, 15, 16, 24. So n is 5. That means there's 5 items in the data set. And the sum of all of them is 77. If you divide 77 by 5, you should get a 15.4, I believe. Now S, I went to the trouble of calculating for you. It's 5.366 using the formulas we've discussed so far. So that's our standard deviation. And our standard error of the mean is S over square root n. So that's your 5.366 over square root of 5, which comes to 2.4. That's our standard error, 2.4. What does that mean? What use is the standard error? Well, we'll get to that. Here's the empirical rule. I'm sure you'll memorize that. So how likely is it that our sample mean is close to what the true mean would be if we had the whole population? This complex function here is called the cumulative distribution function. I'm not going to go into it, it looks horrible. But it's really just to prove that these numbers that I'm going to be showing you soon are not plucked out of my backside. They're worked out statistically. So these give us something called confidence intervals at each multiple of the standard error. In scientific circles, these are called sigmas. Here is the empirical rule then. So if you work out the mean, mu, if you assume there is a mean called mu for the entire population, we don't know what that exactly is because we've got a sample, but there is going to be a mean. There will be a mean height of everybody in the country, but we don't know exactly what it is. Hopefully our sample is close to it, but how close to it? How confident can we be that it's close? Well, if you work out the standard deviation and you add it onto the mean and subtract it from the mean, you get a little bar on either side of it. And that's within one standard deviation of the mean. And that formula I just showed you comes to 68% for this width. So what that tells us is we can be 68% confident that the mean of the entire population is no more than sigma, or one standard deviation, sorry, on either side of the mean that you've calculated. If you want to go for two standard deviations, then it's 95%. I think 1.96 standard deviation to be exact, if I'm not mistaken. And three standard deviations gives you a confidence of 99.7%, which is usually enough for most people, but scientists often go for a 5 sigma confidence. Anyway, this all only works on a bell curve type of data, but hopefully if you've taken multiple samples, it should take that shape. So that's what standard deviation is used for. And that's almost it. Oh, I've just said that, haven't I? Yeah, that's pretty much it. I'll explain some details on how to actually calculate that in the code in another video.